Hello everyone. In this pre-lecture tutorial, we're going to discuss how to assess proposed reaction mechanisms and to determine whether or not those reaction mechanisms are plausible for a chemical reaction. And so normally problems of this type typically either outright give you the rate law for a chemical reaction, or they will give you sufficient information for you to actually figure out the rate law for yourself, and then you would be able to evaluate the mechanism from there. Now, there are also those types of problems where you will actually be given a reaction mechanism, and then you have to determine the overall reaction and isolate any intermediates, and then find out the rate law for yourself from the mechanism itself. We'll be covering both of those types of example problems in this tutorial so that you have a good basic idea as to how to deal with this particular topic. So let's actually jump right into it. Here in this particular reaction problem, I'm given initial rate data for this chemical reaction on the slide. I have 2x plus y going to z, and I have enough information to be able to figure out the order of the reaction with respect to x and y, and then ultimately be able to piece together a rate law for the overall reaction. Now, I'm going to go ahead and just tell you right now that the rate law is actually 0th order with respect to x and first order with respect to y. I leave it to you to go and actually do the method of initial rates as a practice and figure this out for yourself. But basically, the rate law for this reaction should be K times the concentration of Y. They also ask us to calculate the rate constant once we've actually found the rate law. And again, I'll leave it to you to verify as additional practice, but again, the rate constant should be 7.0 times 10 to the negative third inverse seconds. Now, since we have the rate law in hand, now we're asked to go and evaluate each of these three reaction mechanisms and figure out which one is actually appropriate for this chemical reaction and for the data that we've been given. And so when it comes to evaluating reaction mechanisms, you have to keep certain things in mind, and I've listed them out for you here on this slide. First off, the molecularity of the elementary steps should be reasonable, and what that means is primarily you're going to see unimolecular steps and bimolecular steps. It's very rare that you would actually get the involvement of a termolecular step, or a step where you have three molecules coming together and colliding simultaneously, because basically the probability and the likelihood of three molecules coming together with just enough energy to interact and react in such a way that an activation energy is exceeded and the chemical reaction proceeds from there is extremely low. And so for the most part, you're going to get unimolecular and bimolecular steps in these reaction mechanisms. The elementary reactions should also add up to the overall reaction equation. And in general, the overall rate law that you get from the reaction mechanism should match the rate law that is determined experimentally for the chemical reaction. So applying these characteristics to these mechanisms that are shown in this problem, then we should be able to figure out which of these reaction mechanisms, 1, 2, or 3, best fits the data that's provided above. And so let's actually go through, starting with mechanism number 1. So we're asked to determine the molecularity for each of the steps in each of the mechanisms. So this first step in mechanism 1, since it involves two reactant molecules, then this would be considered a bimolecular elementary reaction. Notice that the second elementary reaction in this mechanism also involves two molecules, and so it would also be considered bimolecular. Now, I would also need to figure out whether the reaction mechanism has any intermediates. Now, intermediates are formed during the mechanism itself, but they're consumed within the mechanism so that they don't appear on the reactant side of the overall equation or on the product side. Basically, they should cancel if I add the elementary steps together vertically. So if you sort of mentally imagine me adding these chemical equations together, if you notice, species M actually appears twice, once on the reactant side and once on the product side of the elementary reactions. And so that particular species would cancel because M would be an intermediate. And so that means that if I add vertically from here, I get 2x plus y yields z. So notice that that does match the overall reaction equation. However, the rate law for the slow or the rate determining step actually becomes the rate law for the overall reaction. So that means that here, the rate for the slow step in mechanism 1 is the rate constant, K. Since it's the first step, let's call it K1, times the molarity of X times the molarity of Y. For the fast step, the rate is K2, since we're on the second step, X times M. So the concentration of X times the concentration of M. The overall rate law, as I said just a little while ago, is controlled by the rate law of the slow step, or the rate determining step in the mechanism. And so that would be this rate law. So the overall rate for this reaction mechanism would be K times X times Y. Now notice this does not match the experimentally determined rate law that we actually figured out at the beginning of the problem. And so as a result, it is unlikely that mechanism 1 would be appropriate for this chemical reaction. Let's try the next one. So first, the first step in mechanism 2 only involves reactant Y. So that makes it unimolecular. Okay, but the second step involves a reactant X and a reactant M. So the fast step in reaction mechanism 2 is bimolecular. If I then proceed to look for intermediates, once again we see that M is a product in the slow step but a reactant in the second step. So basically it's formed and then consumed within the reaction mechanism, so M would be an intermediate. And if I then go and add vertically, then I get X plus Y yields Z. Now, if you notice, this overall reaction mechanism, overall reaction equation, does not match the overall reaction equation that I was given to start the problem. And so because of that mismatch, we cannot assume that this reaction mechanism is consistent for this chemical reaction, even though, if we take a look at the individual rates for each step, the rate for the first step would be K1 times the concentration of reactant Y. For the fast step, it would be K2 times the concentration of X times the concentration of M. Since the first step is the slow step, that means the overall rate would be K times Y, which is actually consistent with the experimentally determined rate law, but because of the mismatch with the overall reaction equation, then mechanism 2 would not be considered a plausible mechanism for this reaction. Now let's look at 3. Now again, one reactant molecule in the slow step, so that's a unimolecular. But each of the subsequent 2 steps have 2 reactant molecules apiece, so that means each of those steps are bimolecular. Now, if I take a look for reaction intermediates, M would be an intermediate and N would be an intermediate. And if I add vertically, then I would get 2x plus y gives me z. So then that checks out with the original reaction equation. The rate for the first step would be k1 times y. The rate for the second would be m times x times k2. And the rate for the third step would be k3 times n times x. But again, the overall reaction rate should be controlled by the slow or the rate determining step. So that would be k times the concentration of y, and that also matches the experimentally determined rate law. And so as a result of these three mechanisms, 1 and 2 would not be plausible, but mechanism 3 does actually agree with the experimental data. Now, let's also take the example of a mechanism in which the first step is not the slow step, because if you notice, each of these mechanisms, the first step was slow. Okay, and we treat mechanisms where the first step is fast to be a little different. Let's do a little bit of work here and figure out the overall reaction equation first. So that means I'm going to go and determine any intermediates here. So N2O2 would be an intermediate because it appears on the product side of one step but the reactant side of another. The same thing here with N2O. So that means that the overall reaction equation should be 2NO plus 2H2 is equal to N2 plus 2H2O. And again, the intermediates, since we just identified them, would be N2O2 as well as N2O. These are my intermediates. Now, they want us to determine the rate law, and they warn us that I cannot express my rate law in terms of an intermediate concentration. And that makes sense, since intermediates sometimes can be very difficult to isolate. And so it would make no sense to express a rate law to a concentration of something that I can't typically determine. And so thinking back to the rule that the slow step and its rate law should determine the overall reaction rate, that means that this rate, and I'm going to go ahead and number these rate constants here, this forward reaction in the first step, I'll label K1. The backward reaction, I'll label K to the minus 1, or K minus 1, sorry. For the second step, that'll be K2, and for this third step, it'll be K3. The rate for the slow step should be K2 times N2O2 times H2 because of the molecularity of the rate determining step. But here, N2O2 is an intermediate, so I have to find a way to express the concentration of N2O2 as other variables, especially variables that include the concentration of reactants that I can actually measure. And so the key to doing that is actually this step that begins the reaction mechanism that's actually in equilibrium. Do you see how the reaction proceeds forward and backward? So what I can do is, if this first step is actually in a rapid equilibrium, that means the rate of forward reaction, which would be K1 times NO2, actually no, I think that's just NO squared, all right, that must be equal to K to the minus 1 times the concentration of N2O2. If I solve this for the concentration of N2O2, then that would be K1 NO, concentration squared, over K minus 1. I'm going to use this expression and plug it in for N2O2. So that would mean the overall reaction rate is going to be K1 times K2 over K minus 1 NO squared times H2. This collection of rate constants, I'm just going to roll in to one big overall rate constant and call this K, NO squared, H2. And so that would actually be my rate law that's consistent with this mechanism. Again, I have to find a way to express this intermediate concentration as a concentration of a reactant that I can measure. And so I use this rapid equilibrium by setting the rates equal to each other to do that. They're also asking, lastly, what's the overall order for this reaction? Well, it's second order in nitrogen monoxide, first order in H2, so that means that overall, this is a third order reaction. Okay, so trying to apply these concepts to the follow-up assignment. Again, any questions are more than welcome via email, and we will discuss this further in class tomorrow. Have a good night.